Here I have a piece of copper wire. I'll put it against the white background so you can see it a little bit better here. It's just supported there. And what I'm going to do is run an electric current through this. Now, I have to say this. I don't want anybody to ever try this at home because I have to put quite a bit of electric current through the wire in order for us to measure the magnetic field. Now, this isn't hooked up to anything, so I can, of course, touch it. I'm going to put this little cardboard backing down. And then on top of the cardboard backing, I have a sheet of paper. And the sheet of paper is... has a hole, put the backing down. We're going to sprinkle the iron filings on there in a second. Next, I have some test equipment here. We'll talk about more what this is all doing later. Here we have a power supply. We can supply current through there, and we have the scope and the function generator here in a minute we'll use to drive the electromagnet. We have a few things we're going to do. First, we're going to drive a direct current through this wire. So I have the black lead, which I'm just going to clip down below onto the bottom of the wire. This is a bare wire with no insulation. And then the top one here, I'm going to, I think, put it right here. All right, so I'm going to clip that. Now that we have electric current flowing in this wire right here, you can see over on the power supply over here, we're sending 9 amps of current. So if you know anything about electricity, 9 amps of current is a lot of electric current. So never, ever, ever try this kind of thing at home. It's something that I don't want anyone doing. That's why I'm doing the video, so you can learn from me doing it and you don't have to do it yourself. So 9 amps of current. Now this wire is now generating a magnetic field around it. So we have here a compass. When we bring the compass close, we can see that as I move the compass around the wire, it is now affected by the magnetic field. We'll come on this side. You can see as I go around, here, it's pointed in that direction. When I go here, it starts to move, and when I go around the other side, it's pointed in another direction. I actually have a separate compass. I'm going to show you 2 different compasses so we can just make sure the effect is real. All right, here's a separate compass. I just wanted to do it with 2 compasses just to show you. So here's the compass when I bring it close to the wire. Look what happens when I bring this thing and follow it around the wire. You can see it's clearly affected by some sort of invisible field, which we call, of course, a magnetic field. Around the wire there. If I were to disconnect this, okay, and there's no other magnets around, this is what the compass is doing without any current flowing in the wire. You can see I can move it on both sides, and effectively it's pointed towards north. As soon as I put electric current through this thing, then of course it's being deflected quite a bit as I move around there, right? Of course, the more electric current we're going to learn, the higher the magnetic field, so the more deflection on a compass we have. So the next thing we want to do is see what does this look like, right? Now we know that magnetic fields have to form closed circles. So because of the symmetry of the wire, there's only really one way it can do that. Let's see if our intuition is correct. So we'll sprinkle these guys, right? And it's a little difficult to get it to look perfect, right? Because this is not a super strong magnetic field just with a single wire like this. You can sort of start to see it take shape, but what I'll do is I'll just tap it like this, and now we can see it. Look what's going on here. If you go very close to the wire, you can see it's forming these concentric rings here. So the magnetic field that is formed around a wire is given by what's called the right-hand rule. If the electric current is going in the direction of your thumb, then your fingers are curling in the direction of the magnetic field. Here the positive current is going through the red wire, so really the current's going down through the page, and the magnetic field is curling in a circle in the direction I have here. Now if I tap it a few more times, I can probably get it to even do maybe a little bit more clear, something like this. So the magnetic field around a wire carrying electric current is curling in a circle around the wire, all right? Okay, now we have what we call an electromagnet. So this is a fancy looking device, but basically what it is a coil of wire. So this is a coil of wire wound around a magnetic core there. So as we run the electricity through the wire, we're going to draw pictures in a little while, but what it does is it takes the magnetic field that's generated by the electricity, and because of the way it's wound, it concentrates the magnetic field inside of the coil. And so we have this steel here, so the magnetic field will be concentrated there. The more current we run through the electromagnet, the stronger the magnetic field, and so we should be able to lift objects with this, and that's what we're going to do next. So we'll hook it up here, and what we'll do is we'll connect the power supply to the terminals. Now we have really 2 of them. We have another one on the other side, but we won't be using that one here. And then we'll turn the electricity on and see what we get. All right, so what we're going to do is first of all, we'll take our paper clips, we'll put them underneath here, and we'll turn the current on here, the voltage, up to a maximum of 6 volts. That's as much current, the voltage driving the current here, that's as much as this thing can take. We're at 2 volts now, nothing has happened. 3 volts, nothing has happened. 4 volts, nothing has happened. And we start getting some action around 4 volts. There, here we're up at 5 volts. We turn the current down and we release them here. So we'll try it one more time and see if we can get it to attract there. And as the current goes up, the magnetic field is going up, which is concentrated inside this coil. Let's see what we just go straight up to 5 here. And of course it lifted them all up there. And we can go down to 0 and we can drop them. Now notice what's happening when we go to 0, some of the paper clips are still sort of attracted there. And that's because as the core there is magnetized, when you release the current or turn the current down, some portion of the steel or whatever material is in there, the iron that's in the steel, remains magnetized. And so you can still get a weak magnetic effect even after you turn it off. Oftentimes that will go away after a while. So let me take these paper clips away, and I'll put these lightweight discs that are down there, and we'll see if we can do the same thing. I just think these are just neat to watch. It's really the same exact demo. So we'll go up. See, this is 2 volts, 3 volts. You can see the current here, 1.3 amps right here. This thing can go up to a maximum of 6 volts. It's about 2 or 3 amps there. So we're up there right around 6 volts. This is about the limit of what this thing can do. And you can see not only is it magnetized, but the discs that are down there, once they become magnetized, they are further attracting the other disc down below, as we showed in the previous demos. We can turn this off and we can release this guy. And you can see there's some residual magnetization. Let me just kind of knock these off, right? And we'll do it again. I just think it's worth doing a couple of different times. So we'll go straight up and then straight down, up and down. Now what I'd like to do is remove these and put some iron filings down below and see if we can lift those up and what that looks like. Okay, here we have the iron filings. Let's go up and see what happens here. It's 1 volt, 2 volts. Oh, starting to be pulled up. I think that's kind of a neat little demo all by itself. And up around 5.5 volts, you can see it's starting to lift it up. And then we can release it, of course. You can kind of like make a dance and go up like this, and then down, and go up again, and then down like this. All right, let me disconnect this, and I want to try to see if we can get a picture of the magnetic field inside this electromagnet. All right, now the first thing I'd like to do, first of all, we're going to turn the electromagnet back on, and we'll try to get a picture of what the field is doing here. So here I have my little handy dandy plate here. I'll shake it up here and see if I can slip this thing down underneath and see if we can get a picture. And you can see immediately what's going on here is it's pulled up like this, and you can see that the magnetic field is circular in nature down there. And as you drag this thing through, you can just see the ripple effect of the magnetic field and how it attracts the iron filings. And it's just kind of mesmerizing to watch. Now the next thing I like to do is turn it sideways and see if we can get a profile view of what the magnetic field is doing. All right, let's try it first with our little plate here. We're going to turn the voltage on up to 6 volts. That's about, or 5, let's do 5.5 volts, about 2 amps, 2.2 amps, something like that. So a lot less than what we had before. Here I'm going to put my little thing down here. And you can see, I can't get it too close, but you can see the magnetic field appearing right here. In fact, I think it's going to be a little easier to see. Let me grab a sheet of paper. I think it'll be a lot easier to see. So what I'll do is I'll put a piece of paper on top, and shake it up, and we'll put this right down on top. And you can see the field here. It's kind of coming out and around and entering into the other side. You can see the curved nature of it like this. As we move it around, you can see it kind of sliding back and forth. Now I'd like to do the exact same thing with the iron filings here. So I'm going to open this up. I'll try to hold it steady here and see what we get. A little harder to see. The reason it's a little harder to see is because the magnetic field is strongest inside of that coil, and we're looking kind of at the side of the coil. So it's kind of coming out of one side of the coil, coming around and entering into the other side of the coil there. And that's where the magnetic field is the strongest. It's almost like there's a bar magnet here now. And notice the connection. We're going to talk about the connection between circulating currents and permanent magnets in a little bit. But effectively, the magnetic field is coming out of one end here and going into the other. Outside of this electromagnet, it's actually not that strong. It's mostly concentrated inside the coil. Now what I'd like to do is I'd like to hook my signal generator up to this electromagnet, which can't push as much current, but we can get it to pulsate and see if we can do some neat interactions with pulsating magnetic fields. All right, here we have something really neat. So here we have the electromagnet, and it's being driven not by the DC power supply, but by a function generator. So I can drive different waveforms through here. When I press the button here, I'm going to drive it with a square pulse to turn it on, then off, and so on. So what I'm going to do is I'm going to get down here. I've got the iron filings that I've sprinkled on this piece of paper, and if I can do it without messing anything up, I'm going to push it underneath the electromagnet here. And you can see that there's some residual magnetism going on from before, but it's basically off right now. Now let's see what happens when we turn the output of the function generator on. So we'll turn it on. We can see on the scope here, let's give it a second. It's catching up there. And it's a square pulse. And the period of this pulse here is, I think I put it to 2 seconds. So this thing repeats, this on-off period repeats every 2 seconds. Now, if we take a look at what's going down under here, right, you can see that the iron filings are being attracted and then repelled, attracted, repelled, right? That's just, I think, honestly, so incredibly cool. You can sort of visualize when you see it on, off like that, that the field is coming on and then off, and you can see it directly in the attraction of the iron filings right there, okay? Now let's play with it a little bit more. Let's turn the, what's called the duty cycle of this function generator. So right now it's half the time on, half the time off. So we'll change it. We'll go over here to duty cycle. And we'll change it from 50%, we'll just go down here to like, I don't know, 25% or something like that. It takes a little time to get down there. All right, so there we're at 25%, and let's see what the difference is right here. So now it's on, off, on, oop, looks like it's off. It's off more than it's on. So for 25% of the time, it's gonna be on, and then it's gonna mostly be off. So on, off, and then mostly off, then on, off, mostly off. So let's change the duty cycle the other direction. We'll go up past 50%, and we'll go to, let's see if I can do 70, just type 75%. Let's see what 75% duty cycle does. So this should flip it the other way. Let's take a look at it. So it's mostly on now, on and then off, on and then off, on and then off, and so on. So let's change the duty cycle back to 50%. So that means half of the time the pulse is on and half the time's off. Now let's change the waveform entirely from a square pulse to a sine wave. So we can go over here to waveforms, right? And instead of a square, we can do a sine, and let's see if we can detect what's happening down here. So now you can see it's raising up very gradually and then relaxing. So a sine is a much more of a smooth curve. So it's on and then off and then on, and instead of punch, 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 punch like this. All right, let's check another guy here. In fact, let's increase the frequency a little bit, or the period. Let's just play with this a little bit. Let's see how far we can drive. You know what, let's go to waveforms first. Let's try a triangle wave, see if we can detect the difference in the triangle wave. Let's do that. So you can see it's just on and then going down, just kind of a ramp up and then down. You can see the triangle wave triggered there in the oscilloscope, up to its peak and then down and then up and so on. So let's go back to the square pulse. Let's let it kind of settle down there. All right, let's try to increase the frequency. So instead of the period here is 2 seconds, let's bring the period down to 1 second to make it happen a little bit faster. So we'll go up here to period. And from 2 seconds, let's drop it down to 1 second. And let's see what happens. So on, off, on, off, and so on. So we're increasing the frequency. I actually don't know how fast we can drive this thing and see the results of it. Let's just try half a second. Let's go over here to period, whoops, period, and we'll go 0.5 seconds. And we can just see it going much, much, much faster. All right, and let's go over here and let's drop it down to 0.25 seconds. So we'll go 0.25 seconds. We're making it shorter and shorter and shorter and shorter, like that. Boom, 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 boom. Now let's change it to a sine wave just for giggles. We'll go to waveform. We'll change it to a sine wave at this higher frequency. We can see how it's going up, down, up, down, up, down, up, down, like that. All right, let's go back to a pulse. And of course we can, now that we're increasing the frequency, we need to change our scope so we can see it a little bit better. All right, now let's go over here to waveforms. Let's go back to square wave. And instead of 0.25, let's go to 0.1 seconds. So a tenth of a second here. Ooh, look at that. Boom, 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 boom. It's like a beating heart, super fast beating heart. All right, how far can we go? I actually don't know. 0.1, let's go 0.05, I guess. 0.05, that's cutting it in half again. Let's see what this looks like. Seconds. Whoa, check it out. It's fluttering. Oh, that's so neat. I have not actually practiced this ahead of time. I mean, I did it, but I didn't try all the different frequencies. Let's drop it from 0.05 to 0.03. 0.03 seconds. And now it's just so fast that we can't even really tell. Let's change it to a sine wave and we'll wrap it up. We'll leave it at this frequency. We'll change it to a sine wave and see what we have. And it's, again, it's so fast, it's flickering, it's so fast that we can't really discern. Here is iron filings. We're going to do a lot with iron filings, but here is just a fluid-filled box here full of iron filings. So with no magnet inside, you can see what's going on here. Let's drop this thing in here and see what happens. We'll drop it in there and look at what happens there. The magnetic, you can see the magnetic field immediately appear. In fact, it's a little more impressive if I close it off here, and you can see it's sort of attracting inside of there now. And if I give it a nice little shake, and I'll try to get the angle with a couple of different cameras. So there's sort of a side view there. Let me kind of let it go so you can sort of see that. And then we'll do it with sort of the top view there. And so you can see that it's the field is exiting and coming around. You can see the curved nature of the field as it comes and sort of enters into the bottom. So we're going to draw more pictures, but I think this is like the best thing that I really want you to drill into your head. Look at how the field is very curved like that and kind of like angular and then going into the bottom. So if you can imagine these lines coming out of the top and then flowing into the bottom, then the next thing you need to know is that the magnet is the strongest, or the magnetic field is the strongest where these field lines are concentrated. So you can sort of see, actually, well, let me go ahead and let it do its thing. But you can kind of see that the bunching up is starting to happen near the ends. So if you can imagine all of these lines entering into the pole, then they're all going to get crowded near the pole, either the north or the south pole. And the more crowded or the more dense those field lines are, the stronger the field. And you can kind of see it now that I've just sort of let it settle right here. You can see along the bottom a really nice curved, you can see that sort of the curved magnetic field's like less dense there, but near the poles everything is bunched up. That's because there's more field lines kind of concentrated there, and so a higher field strength. Here is what we call iron filings. Now we're going to use these a lot in just a few minutes to visualize the magnetic field here, but I do want to share with you and just show you how it's just sort of fascinating to watch. You bring a magnet near this iron, which is able to be magnetized, and you can just see it almost vacuuming it up like a, just like a vacuum cleaner. And you can kind of hang them off of, notice that the iron, the pieces of iron that are attached to the bottom are temporarily magnetized, able to attract further pieces. So it's able to temporarily magnetize the iron. Now eventually the little stalactites, or whatever you want to call it, they get so long that they can no longer pick up anything else, because it has to be close to the parent magnet in order to be magnetized. So the effect does wear off. You can't build these things forever, but we can do some impressive things. Like, that's pretty neat. Now we can kind of hoover them all up here. Let me hold that down, and let's just pick them all up. That's just kind of neat to look at. You can just see the back and forth dancing that's going on here as we pick them up there. So we can kind of do that. Drill it home that there is some sort of invisible field around this, because if we have a compass, let me move the magnet away, this compass is going to point to the magnetic north pole of the Earth in my vicinity. So you can see it's kind of pointing off in that direction. So notice it's pointing in that direction. If I move it over here, it's pointing in the same direction. If I move it over here, same direction. Over here, same direction, because it's pointed to the strongest magnetic field that it feels, which is the Earth's magnetic field. So no matter where I move it, now if I bring a new magnet here, there is a magnetic field emanating and permeating and surrounding that space here. And now let me move this over here, and we'll put this over here. And what happens as we get closer to this magnet, right? You can see it's sort of locked in place. Let me move the magnet out of the way, and we can see that the effect that it has here. Let's move it over here. Now it's pointing to the magnetic north. As we put the magnet here, you can see it just change. Now as we move the magnet around here, you can see it's just locked on. It's locked on to what it sees nearby, because the magnetic field coming out of this thing is much, much stronger than the locally, because it's closer to the magnetic field of Earth. The magnetic field of Earth is strong enough to protect us from the solar wind, and it's a strong magnetic field. But locally, this magnet, since it's so much closer, is kind of overwhelming it here. Now, as we move farther away, it does continue to respond, but notice it's kind of like wiggling more. It's maybe not like quite as locked on. It's moving, but it's just not as locked on. When you bring this thing close, it is absolutely locked on to moving as we move around here. So here we have our north-south magnet. Remember, this is the one that's not so strong. So I'm going to place it under a sheet of paper, and I'll sprinkle these iron filings on top. And when we sprinkle the iron filings on top, hopefully we will see the magnetic field that this magnet has sort of like come into focus here. We'll get a few more on there. I can start to sort of see it now. Yeah, you can see that good. And you could give the paper a little, kind of a little shake, helps it also, right? So you can see that here was the north pole of the magnet. You can even see the S for the south here. That the magnetic field is emanating from here and going and traveling around and entering in through the south pole, and the same kind of thing is happening right here. Right? This is very, very similar to what we already saw with our cube magnet. I'll put it right on top. In 3 dimensions, you can see it's happening going from north to south in 3 dimensions all throughout space there. This is just a flat representation of the same thing. So let's go and do the same thing again with our stronger bar magnet. All right, here's our stronger bar magnet, and we'll put it underneath, and we should basically see the same sort of thing, but I just want to give you exposure to what it looks like, but it should look a little more intense. We'll kind of like see. Notice how when we sprinkle it, we don't have to shake the paper. It's like immediately locking into place. It's like a really, really, really nice looking magnetic field here. And that's because this magnet is stronger. So as soon as the iron hits the paper, it's immediately magnetized and locked into place. We can give a little shaking here or whatever if we want to see it. But you can see how intense the magnetic field near is the north and the south here. All these field lines are coming and entering into the north and the south pole. The density or the flux density of the magnetic field dictates how strong the field is. So the field is strongest here, and it's weaker here. And of course, as you go farther out, the field lines are spread even more farther out, and so it's weaker out there. I have one more, even stronger bar magnet. We'll do that one next. All right, now this one's not labeled north and south, but there is a north and a south pole here. I just don't know which is which, but it's there. This is called a neodymium magnet, which is a rare earth magnet, and it's stronger than any of the other ones. So put that under there. Let's see what this looks like. We should see the same thing, but we should see it lock into place really, really quickly. Let's see. Notice that this one is so strong that we can't even really visualize the field that much. The reason you can't visualize the field that much is because it's attracting it so incredibly fast that you really can't see much of anything. It's just attracting it to it. Now you can sort of see the shape of it. You can see that it's radially coming out here. But again, it's so strong that it's just pulling it in immediately. Now this one is actually so strong. I want to show you what happens when I lift it up. Just because of the iron there, I've actually lifted the magnet off of the underlying paper here. If I reach down below, it's actually attracted. It's not even going to come off the paper. You can see me trying to pull it. It's very difficult to pull it off. This is a really strong magnet. In fact, we can see what it looks like to try to suck these guys up over here. You can just see it, just like a vacuum cleaner. You can just pull it all up there. All right. All right, I have another cool toy here. This is iron filings inside of a sort of a transparent plate there, and there's sort of oil or fluid in there. And if you shake this thing up and just kind of get it going, then you can get it to evenly disperse throughout there. It's just different ways of visualizing things. If I'm going to do this, I want to do it right. I want to do it with a bunch of different ways to visualize. You're going to see the same thing, but it's just really neat to see this just sort of snap into place. Let's look at the magnetic field right there. And you can see that the magnetic field sort of snaps into place. You can give a little shake. Now remember, this is our less strong magnet. Actually, I think it's going to work better if we go this way. So let's go long ways here. We'll go right down on top of it, and let's see if we can see the magnetic field. And you can. Of course, you can see it emanating and coming from one pole into the other, from the north, coming out into the south, same sort of thing. Let's do the same exact thing with our slightly stronger magnet. We'll, again, go this direction. Now let's make it north-south like this. See what this looks like. Okay, we'll go right on top with it, and you can see it. You can see the magnetic field coming out. Notice it's so strong that you can't see it after a few minutes. So when you use this one, it's actually a little bit better to kind of keep it separated from maybe that far away. Then you can really see the field very, very, very clearly. And check it out. As you move it around, it's so neat to watch the field sort of propagate through the iron filings. In fact, that's so cool. I think we're going to do it again. So we start over here this time, and let's just sort of race through and watch the magnetic field propagate through and affect the iron filings that are above, like that. So we'll do the same thing. We'll see how fast it happens. Boom, it's just done. It attracts it so fast you can't really see it. So what we can do to visualize it a little better is, because we couldn't really see it better before, we could just keep it separated from the top, like maybe this far away. Then it's still starting to suck it in from all directions. In fact, this one is so strong, it's emanating very far away, so we're going to see it better when we turn it lengthwise, like this. Well, let me mix these iron filings up a little bit more. Let's see if we can see it right there. You can see that magnetic field really, really, really clearly. Get a little closer, and you can just see it starting to suck it in there. So that's a neodymium magnet, which is a rare earth magnet. Okay, here's our disc magnet with the circle in the middle. Now, it's not labeled north and south, but I can tell you how this works is that one side of this disc is the north side, and the other side would be like the south side. Now, I don't know which is which, but one of them is north and one of them is south. So if you can imagine, the field is coming out of the north side and entering into the south side, but it's doing that all the way around. It's coming out of one side of the disc and going around to the other side, and also going through the center and reaching around as well. You can almost think of it like if this is the north pole here of a bar magnet, we know that the field comes out and into the south side. It's just this one is constructed in a way where we take the bar magnet, you make it really, really small, and then you make a disc of it. So it comes around like that. Let's see if we can visualize the magnetic field using our iron filings and see if we can see if our idea makes sense here. So we have the bar magnet there, or the circle magnet there, put some iron filings on top. Now it's going to be difficult to see the full extent of it because we're looking kind of down, right? As we said before, it's coming out of the top, going through the table and back through the bottom. So we're not really able to see. You would have to look from the side to be able to see the profile. Maybe we'll try it. I think it's going to be difficult to see, but maybe we'll try it anyway. And we can see that it's doing something like that. We can do the same thing with the fluid cavity. All right, here we go. Take two. We'll put this guy right on top, and we see, oh, that's so neat looking. It just sort of, you could just see it happen like in real time. We'll do that one more time. If I go all the way on top of it, it just happens too fast. I almost prefer to keep it far away so you can sort of see it happen. Starts to attract those guys. You can see the middle clear out because it's just sort of stopping as the filings get to the edge. They're sort of stopping there. And so the field lines are coming out and going around to the other side. Now, I don't really know if this is going to work, but let's see if we can get this to work. I've never tried it, so I doubt it'll work, but I don't know. Let's just try it. Let's just try it. Let's see what it looks like when we do it from edge on. Oh, look at that. That worked way better than I thought. I hadn't actually tried this before. So you can see the magnetic field is coming out of one side and into the other side. So one side is north, the other side is south, or vice versa. We'll do the same thing, just for giggles, with the fluid-filled cavity. All right, here we have our disc magnet. We'll put it like that. We'll do our fluid-filled cavity and see what we can see. We'll get it close, and what do we see? Yes, it's exactly what we want to see. So we You can see it kind of coming out and reaching around to the other side. So that is the shape of the field. Now you have to use your imagination because it's happening in 3 dimensions. All around the periphery, it's kind of coming out and also going through the middle and doing the same kind of thing there as well. All right, what other magnets do we have? We have a horseshoe magnet. This is a kind of a weak horseshoe magnet. When you see a horseshoe magnet, you need to think basically all that they've done is they take a north-south magnet here and they just literally bend it and they heat it up or something and they bend it into a horseshoe. So it's nothing, it's not like a different kind of magnet or anything. It's just a bent shape. And of course we can do it with our handy-dandy little visualizer right here. And we can see that the north and the south sides here, we have the most concentrated area there. And of course the north is kind of connected to the south in the same way that it is here. The field is coming out and into the other side, so of course it's going to come out and go into the other side there, but of course it also has to travel and go all the way around here, all the way around the magnet. It's a little bit weaker on this on the bottom side there. Let's try it with the iron filings. I haven't actually done this one, but you know, we've got everything ready. And I have a stronger horseshoe magnet we can visualize as well. So we'll do the same thing here. You can see the field is definitely strongest between the ends of the north and the south. But if you can visualize it, it's kind of connected there, but it's also kind of going around very, very weakly down to connect to the other side as well. All right, here's our final horseshoe magnet here. We've got this one here. We'll go first from the top view here. What does our little magnetic plate here show us? Of course, this is a lot stronger, so we can see the flux density. The density of the field lines is much, much tighter there, or more concentrated, so we know that this magnet is stronger, and it is a stronger magnet. We'll look at it with the iron filings. I'm getting kind of efficient at this, so I can kind of got the hang of it there. Let's see what it looks like out here, away from it. So the field does, of course, go between. That's where it's strongest, but it does loop around and connect to the other side. So remember, magnetic field lines have to form closed loops. We'll do it from the side view, just to close it out and finish out this part. All right, so here we have the profile of the horseshoe magnet here. Again, we should see the north and the south connected together. We'll try it with this first, see what it looks like, and that's exactly what we see. The north and the south pole are connected by these field lines, and of course the lines go all the way around, but they're a little bit weaker as they get farther away. There. So we'll do the same thing, and this will be our last iron filing demo. A little sad, I know, but that's what we're going to do here. So you can see, same kind of thing. The way you read this is you say, all right, obviously it's stronger here where everything is concentrated, but as we get farther away, the field lines are a little more spread out, and so it's weaker, but ultimately it is connecting the north and the south pole, and all of these magnets form closed loops. The first thing we want to talk about is what everybody knows and is interested in, and that is that magnets attract and repel each other. So here I have 2 bar magnets. Notice I have a north and a south pole, and you can see that when we get them close together, these guys are, it looks a little bit better this way, that they repel each other. Notice that when you have south facing south, they repel each other, but when you turn it around to a north side of the magnet, then of course it doesn't repel each other anymore, it attracts each other. Now we have a little bit stronger magnets here. Look at these. These influence each other farther away, and they just look magical the way in which they work. So here we have the 2 north sides facing each other. If we put the 2 south sides facing each other, we get repulsion. So like sides of the magnet repel each other, but when we have a north facing a south side, it doesn't repel each other anymore. It attracts. So here we have a magnet attracting and repelling another magnet. If we turn them sideways, we can get similar behavior. South touching north, north touching south, they attract each other, and it's very strong, actually hard to pull apart. But if we turn this around so that we have south and south facing and north facing, then of course, this is really impressive and fun to do. They just totally repel each other. You can get, you know, in this case, several centimeters of distance between them there. I have over here these disc magnets with a hole in them, and even though they're not labeled, there is a north and a south side. It's not labeled, but there's a north and a south side to this, and you can see that these are magnets also. Attract the magnet there. Now the interesting thing we can do is we can connect them like a car, and we can actually use the magnet underneath to sort of propel the wheels, so to speak, on the car. So let's see if we can get that to work. And if we kind of push it over here, there's a little bit of repulsion I'm feeling, but then when I get past it here, you can kind of see it kind of like scootering that way. So what's really going on is it's sort of, it's attracting it here, and then when it gets to the middle of the magnet, I'm starting to feel a repulsive force, but when it gets over the hump of the repulsion, then it's kind of pushing it. You can see it kind of like oscillating back and forth right there. That's kind of neat too, actually. You can see that effect right there, because there's an attractive force right there. out of the North Pole of the magnet, there is an invisible field that is coming out of here and entering into the South Pole, right? You can't see it, but we see its effects by its attraction and repulsion of other magnets and other metals. And the field is actually coming out of the North Pole and entering into the South Pole. So the directionality makes it a vector field. So if I put this guy on the bottom here and then put this one on top, then I feel a repulsive force, and you can see it's basically levitating right there. Now what's neat about this is I can sort of bounce it up and down. I can feel it. It's like very springy. It's like a mattress or something. It's very springy here. So here we have some paper clips. These are coated, so they're colorful, but inside, of course, they're metal paper clips. And then we can take the magnets and actually, even though these are not magnetic, you can see they're not attracting each other, we can obviously use a magnet to lift them up. Now this is a pretty weak magnet, but still works pretty good. Let's grab our stronger magnet and see how that looks. We'll just kind of bring this down here and we get a little closer, and of course we start to pick these guys up. And I think we even have a better magnet probably for this demo. These are already together, but we can just get it a little closer and we can immediately see. That's pretty neat. We'll do that one more time. So you can see that as the magnet is stronger, it can exert a force over a longer distance, a magnetic force. But what's interesting about it, so there are different materials that are able to be attracted by a magnet. We call those magnetic materials, and some materials are not, right? For instance, some examples. Iron is magnetic. Inside of this container is little filings of iron. All right, so here I have some copper wire. There's no insulation on this, so that's why it looks beautiful in copper there. We're actually going to use this wire later to make our to run an electric current and see the magnetic field that surrounds a wire. That's why I have it out. And here we have our paper clips. Now, if I run, of course, the magnet over the paper clips, of course they attract, but I can run my magnet along the copper all day long, and nothing happens. It's not magnetic at all. This is the more strong magnet I have. It's just not affected by it at all. Aluminum is the same way. Copper and aluminum and some of the others are not able to be spin aligned from the outside like this, whereas whatever this paper clip is made of, probably steel or something, are the electrons that are in there. It's not magnetic now, but when we bring the magnet close to it, it's able to align the electron spins in these paper clips, and then so they become magnetized, and of course magnets can be attracted, and so it attracts. If you take this guy, of course you can attract them. And notice what's happening here. This is actually kind of interesting. Notice that let's look at the one on the end here. The one on the end is able to be attracted to the one next door. Even though the one next door, let's remove these two away from the magnet. Are these magnetic? No, they're not magnetic. So these two little discs here, they are not magnetic, right? But whenever they are touching one of the pieces that are touching the magnet, then they're able to turn into magnets. So what's happening whenever you attract a piece of metal is the magnetic field emanating from the permanent magnet, where I'll just give the punchline away. And the permanent magnet are materials where all of the electron spins are already aligned in the same direction, or a whole great many of them are aligned in the same direction. So the magnetic field can emanate and permeate the space around the permanent magnet. Whenever you have a material come into contact with that's able to be magnetized, then temporarily their electron spins can be aligned in the same way. So they can turn into magnets sort of temporarily when they're in the vicinity of the magnetic field. But when we remove these guys from the magnetic field, as they're all sticking together here, we can just kind of like pull them away, and then suddenly everything literally falls apart. They're not magnets anymore. So sort of a temporary effect. So what I want to really drive home is that magnetism and electricity are really two sides of the same coin, really. And that's why you hear electromagnetism thrown around so much. Electric current can generate a magnetic field. Later, we're going to learn that a magnetic field can actually generate an electric current also. That's not part of what we've done here, but it's something we'll do later, right? But I want you to understand that understanding how a coil of wire concentrates a magnetic field inside of it is how a lot of our modern technology works. Motors, generators, and other devices run on this concept. And as we talk about permanent magnets, which we'll do in just a few minutes, we're going to talk about how the motion of the electrons are mimicking little coils of wire, so to speak, to generate the magnetic field in a permanent magnet. So let me take the demo equipment down and we'll draw some pictures of magnetic fields and tie everything together that we've learned through the demos. So here we go. It's going to be easy to understand, I promise. Here is a bar magnet, right? Here is another bar magnet. All bar magnets have some north and south pole. I'm going to draw this one north-south. I'm going to draw this one north-south. Now, how are these things going to behave? Same poles are going to repel each other. We know that to be the case. Let's draw the magnetic field, not the whole field. We'll just draw kind of a little portion of it. It comes out of the north, goes into the south. So this way, this way, this way. It goes out of the north, into the south, right? This one is going to go this way, and it's going to connect again to its south pole, out of the north, like this, and in to the south. Right? Now what's going to happen as we push these things closer together? Notice that the direction of these arrows are kind of pointed at odds with each other, but the closer I get them, what's going to happen is they're going to be sort of additive. Yes, you can think of it as a vector. You can think of it, some of it pointed this way and some of it pointed up. So you are going to have a cancellation in the portions that are pointed at each other, but you are going to have a portion pointed up. And as you get them closer together, that's going to get bigger and bigger and bigger. So they're going to be additive inside. They're in general pointed in the same direction. So you're going to have strong field inside of here as you push them together, because you can see they're sort of pointed not exactly in the same direction, but as they get closer together, they're going to be more and more, if you can think about the ones coming this way, they're going to be aligned up more and more, and it's going to get very, very strong magnetic field in the center. But the stronger the magnetic field, the more energy is stored. So you have to think about, how does the universe operate? The universe operates by going from high energy to low energy. This marker has potential energy from the gravitational field of Earth. Here it is at a high potential energy. When I let it go, it's going to move down to a lower potential energy because it's closer to the ground. Everything in general wants to travel towards lower energy. If you start asking me questions like, well, why does everything try to go to lower energy? I am sorry, I can't help you, but that is how our universe works. The rules that are in place are that things tend to wind down towards lower energy. When you drop things, they go from high energy to low energy. When you have temperature, a very hot cup of water, it tends to cool off because it's going from high energy, high movement of the atoms, to low energy, low movement of the atoms. When you stretch a rubber band, that's high energy. You let it go, it goes to low energy state. And if you try to push these magnets together, it's going to be trying to make a stronger and stronger magnetic field in the center, which is going to raise the energy of the the energy stored there. And the universe never wants to go to a higher energy state. That goes against the laws of nature. So when you put two magnets together, because the magnetic field is trying to get stronger in the middle, storing more energy, it's going to resist that. In other words, I have to put work in to store the energy there. Let me say that again. I have to put work in from my chemical reactions in my muscles. I have to do work on the magnets to store the energy that is now higher between the magnets. Because when I put them together and force them together and hold them there, then I've now stored energy in the field. Where did the energy come from? It came from my muscles. Where did that energy come from? It came from the food I ate. Where did that energy come from? The chemical bonds of the food I had. So the energy came from somewhere, the food, and into the magnetic field. When I let it go, they tend to push apart because the energy is then released, and everything, the universe tries to move towards lower energy states. Just like the marker goes from high to low, the child on the slide goes from high to low, the rubber band goes from high to low, the cup of coffee goes from hot to cold. High energy to low energy. That's why they repel, because as you push them together, you're trying to make the field stronger there, which means more energy there. It's like trying to go uphill on a slide. You're going to have to fight and do energy and work on yourself to climb a flight of stairs. That's just the way the universe works. Now, let us talk about the opposite situation. Let's talk about the situation where now I have two bar magnets. And instead of this, I put this as the North Pole here, and I put this as the South Pole here. You already know what's going to happen. Opposites attract, so they're going to come together. Let's see if we can understand it. The magnetic field exits and enters here, exits and enters here. It comes out here and enters here. It comes out here and it enters here. It goes out of the North Pole, always into the South Pole. So out of the North Pole, always into the South Pole. And then it goes out of the North Pole here, out of the North Pole here, and this direction, and into the South Pole here, into the South Pole here. Now I'm going to erase this one because I think this makes it confusing. But you can see the arrow actually, let me erase this one as well. I think it's going to be a little clearer if I put, yeah, like this, like that. So like this. Notice the direction of the arrows. When I bring these things closer together, notice that this one is going up, but this one at the same location is going down. They're fighting each other. And as I bring them closer and closer together, I messed up my drawing, I'm sorry about that. As I bring them closer and closer together, what is going to happen? This magnetic field is going to tend to cancel with that one and make the magnetic field strength lower. This one is going to be going opposite direction of this one, and it's going to tend to make the magnetic field strength lower in the center here. So as I bring these guys together, I'm going to write down weaker. As I bring them closer together, the field gets weaker in strength. But weaker in strength means weaker in energy storage. And remember, the universe likes to go towards lower and lower energy storage. So two magnets attracting can be explained. Because when we bring those two poles of the magnet together, we are canceling the magnetic field, making the magnetic field lower between them, which is a lower energy state. Lower energy, it's like releasing energy from the rubber band. The same way the rubber band comes together, the magnets come together, because as soon as that energy starts to get lowered, it is just going to fly together to make the energy lower. Forces in nature generally always push things in the direction of lower energy. Gravity pushes you down the slide to lower energy. The electric forces pull us to lower energy from the rubber band, and the magnets pull each other together or push each other together into a lower energy state together where the field is weaker. You feel a repulsive force because as we try to do this, the field is stronger and we're raising the energy here, and so it wants to resist that. Okay, that is about all I want to say about it. I can talk about magnetic attraction and repulsive in other ways. You can use relativity theory to talk about relativistic effects to explain why magnets work. And I probably will do that one day because I think it's a neat way to look at it. But it's just another way of looking at it, right? An alternative way of looking at it. You can also look at the magnetic force on a charged particle, the deflection of a charged particle from the magnetic force itself to explain why magnets attract each other. That's another fine way of doing it. I thought about presenting all of those, but ultimately I think that this is the most clear and elucidating, to use a big word, way to explain it. The universe likes to go from high energy to low energy. When you push two magnets together with the same pole, either both north or both south, the same exact thing will happen if you take this. If you can imagine the south pole over here, they're both going to be pointed in the same direction, and the two south poles are going to make a strong field, and it resists that. But if you flip it around, they're going to attract to make the field and the energy stored lower. Now, if you ask another question, well, why does the energy of the universe like to get lower? Well, I don't know, and nobody knows, right? Or you might say, back to the electron spinning. You might say, okay, that's a neat theory about the electron spinning and how it explains magnetism, but why do electrons spin? I don't know, okay? And also, is it a ball? No, we know it's not a ball. Quantum mechanics is a wave theory. We know electrons are waves, but they have some kind of angular momentum, and nobody has a really good picture to describe how a wavy thing has an angular momentum, which we usually associate with spinning objects in the macroscopic level. Ultimately, one of my favorite people that I've ever studied is a famous scientist named Richard Feynman. Probably knew more about quantum mechanics than most people will ever learn, right? Way more than me. And somebody asked him, hey, explain to me why magnets work. And he thought about it and he gave about a 20-minute answer and ultimately concluded, I can't explain it to you because once you continue asking questions, you get down to the point beyond which anyone has any answers to anything. So all we do in science is we have models of nature, right? Do magnetic field lines exist? Not sure. They're a great calculational tool to calculate how things will behave though. Do electrons really spin? Not sure, probably not. But it's a great calculational tool. It's a good model of how the universe works. Maybe everything is string theory. Maybe everything is waving strings. Maybe angular momentum is something totally different than I can conceive of. But that doesn't make the theories and the ideas worthless. We come up with better and better models to describe the world. This is how I chose to describe how magnetism attracts and repels objects to you. When you bring a magnet next to the paperclip, it aligns the magnetic domains as we drew in the paperclip. And then now we've explained how magnets can attract and repel, and then of course they attract each other. So you're inducing a magnet to form, and then they attract each other. And then of course we talked about this. If that doesn't satisfy you, well, join the club. It doesn't totally satisfy me either, but I think it's the best humanity can do. with just making better and better models to describe our world. I hope you've enjoyed this. I know it was a bit long. I thought about cutting several things out, but ultimately I thought, you know what, I'll just put it out there and see what people think. So please drop me a line, let me know what you think, and if you made it to the end, thank you very much. Drop me your thoughts, and I'll see you in the next one. Learn anything at mathandscience.com.